everyone. I did my material science project on rutile TiO2, and titanium dioxide is a naturally occurring oxide of titanium that occurs in three crystalline forms: brookite, anatase, and rutile. However, it is not naturally occurring in nature and is usually derived from ores of ilmenite or leucoxene. The rutile and anatase forms both have a tetragonal crystal structure, while the brookite form has an orthorhombic structure. Both the anatase and rutile TiO2 are widely used in industry as opposed to brookite. Titanium dioxide is a ceramic material that exhibits ionic bonding, and the coordination number for both the rutile and anatase crystalline structures for the titanium cation is 6, while for the oxygen anion is 3, and the difference between the crystal structure is that the anatase is less densely packed. Rutile TiO2 appears in a dark reddish color, but when finely ground to a powder, it appears bright white. Titanium dioxide is chemically stable, non-flammable, biocompatible, non-toxic, and low cost, which is why it has many applications and uses across many different industries. TiO2 exhibits semiconducting behavior and has a high refractive index, which allows it to absorb or reflect the UV rays. It also demonstrates high fracture toughness, hardness, opacity, and corrosion resistance. Its electrical resistance changes with the interaction of certain gases at high temperatures, which has applications in sensing and monitoring of gases. Rutile TiO2 is optically positive and has high birefringence, which means incident rays of light can be split in two rays when in contact with titanium dioxide. And here's a listed table that shows the different values of titanium dioxide, different mechanical properties from density to fracture toughness, shear modulus, thermal conductivity, and refractive index. Before we get to applications, I will show my 3D model, and this is just a website that has a better 3D model for more accuracy, in which I modeled my 3D model after. Here is my 3D model. It has the titanium atoms in the blue and the oxygen atoms in the red. The titanium atoms are almost 4 times larger than the oxygen atoms, which is why the difference in size appears this way. I tried drawing the bonds using cylinders and painting them white. And one thing about the tetragonal structure is the distance A and B are the same length, but the distance C is much longer. Back to the presentation. The bright white color of pulverized rutile titanium dioxide makes it very useful in the production of white pigments due to its non-toxicity. It can often be used in cosmetics, sunscreen, papers, inks, and foods. Since the pigment is opaque and bright white, it can be used on glass coatings, porcelains, and paints as well. TiO2 is mainly used in pigment applications, and that's where it sees its widest use. Since TiO2 exhibits corrosion resistance, its coatings are used to enhance the corrosion resistance of other materials, such as steel and petroleum tankers, or in nanoparticle thin film applications. TiO2 has applications in the medical field due to its biocompatibility and non-toxicity. Titanium dioxide is coated on implants, which allows the implant to better bond and connect with the surrounding tissue, improving cell adhesion. Titanium dioxide nanotubes were found to increase cell attachment and bonding to implants, and could even be used as biosensors within the body. TiO2 also exhibits high wear resistance due to its high hardness and is often used for coatings in pump seals and propeller shaft bearing sleeves. It is shown to improve the mechanical properties of the materials that it is dispersed in as well. Under UV conditions, TiO2 can produce disinfecting and self-cleaning properties, making them good antimicrobial coatings. This extends its applications as a coating from the medical field to air filters or any other similar sanitary surfaces. Titanium dioxide can be used in sensing and electrocatalysis. At high temperatures, the electron transfer at the surface of TiO2 leads to an increase in sensor resistance in the presence of air. Comparing its resistance in ambient conditions in relation to a test gas, a change in electrical signal can be detected and used in sensing and monitoring, which is a result of its semiconducting properties. Photocatalytic oxidation, or PCO, employs the use of a photocatalyst in the presence of UV light to break down volatile organic compounds, VOCs, and other pollutants into less harmful substances. TiO2 is widely used in PCO applications as the photocatalyst in order to reduce the amount of VOCs and other pollutants in the air to more acceptable levels. Much research on the application of PCO in air filters is still being done and presents a promising future. Rutile TiO2 in its pure form is actually less effective than anatase TiO2 in PCO applications due to a larger band gap in the anatase form. However, both forms are commonly combined into a form of TiO2 known as P25, which is about 75% anatase and 25% rutile. One concern about the use of PCO in air filter applications is the formation of harmful intermediates such as formaldehyde as a result of photocatalytic reactions that occur due to the titanium coatings. And another concern is the necessity for a UV light source as compared to simpler mechanical filters. And these are my sources. Thank you very much.